All right, welcome back. So we'll continue now. In the last segment, we've studied about balance of linear and angular momentum. We also looked at a couple of properties of the Cauchy stress tensor, right? We looked at, in particular, we looked at how it can, how it admits the eigenvalue decomposition, and how the notion of the eigenvalue problem is arrived at by asking the question of how to find extremal values of the normal stress. Okay? What I want to do today is just complete in this segment just a few more things about the stress. Okay? All right, so we're continuing here we're just talking about the Cauchy stress. And in particular, we are going to talk about things that are related to the fact that the Cauchy stress is a tensor. All right? So, recall, first of all, that the Cauchy stress is symmetric. Okay? Recall this and the eigenvalue decomposition. Right? Or really the eigenvalue problem. Okay. And the eigenvalue problem for the Cauchy stress is this one, right? Sigma, we wrote it back then as sigma n equals lambda n, right? Where n belongs to R3. It's a vector. Furthermore, it's a unit vector. Right? And we saw that lambda belongs to reals, right? In particular, the fact that the stress is symmetric tells us that indeed lambda is a real number as against a complex number. All right? So we have this, and now you may recall that earlier on when we studied kinematics and we looked at quantities such as the right and left Cauchy-Green tensors and the stretch tensors, we said that the fact that those objects are symmetric says that from the eigenvalue problem, we can also write a so-called spectral decomposition of them. All right? So, and this is the case with the Cauchy stress tensor also. It's a symmetric tensor, and therefore it admits the spectral decomposition. Okay? So we can say that sigma has a spectral decomposition. And now just for distinctiveness from the way we wrote out the spectral decomposition of the various stretch tensors, I am going to say, so if we write the eigenvalues, say lambda sub A equals sigma sub A, for A equals 1, 2, 3. All right? We're just relabeling the eigenvalues. Okay? If we do this, then we now write out the spectral decomposition as follows: sigma equals summation A equals 1 to 3, sigma A NA tensor NA. All right? And here, of course, we know that sigma A, the sigma A's are the eigenvalues and the NA's are the eigenvectors. We are in the context of mechanics, the sigma A's are also referred to as the principal stresses. right? And the NAs are then the principal directions. Okay? All right. So that's one thing I wanted to say about the Cauchy stress tensor. The next thing is just let's think about particular states of stress. Okay? Let's suppose that we have a we have the body of interest, and let's suppose that we are looking in every case at uniform stress states. All right. So what this means is that the stress is uniform over the body. Right. So if we have our basis, we have the body in the current configuration, right? And we have a stress sigma, and let's suppose that the loading on the body and so forth are such that the stress is uniform over this entire body. Okay? So in the context of using our props here, we have our basis, we have our body in the current configuration, because we are talking about the Cauchy stress, which is defined on the current configuration, and we're saying that whatever it is that's happening to the body, the stress tensor is uniform throughout, right? At every point in the body, you would find the same stress. Okay? That's the situation we have now. Okay, so consider uniform stress states. Okay, so what this means is that sigma as a function of position and time, because it is a spatial function after all, is just a function of time. Just to keep things simple. Okay, there's no significant laws of generality for what I want to say here. Okay, so all I want to do is to point out that now if you talk of a uniaxial state of stress, okay, all right, so let n be a vector as we've always used, and be a unit vector. Okay, so if we have a stress tensor where sigma is written as, let's say, sigma bar n tensor n, this is a uniaxial state of stress. Okay, we've written it in this fashion using our dyadic notation, our tensor product notation, and the fact that we know that we can expand the stress in terms of its in terms of an an orthonormal set of vectors. That's what we've done here. If you compare this with our with the way we wrote tensors in general, by expanding them in terms of the basis, you will see that what we've done here is pick effectively just one of those basis vectors. Okay. All right, so this is how you write out a uniaxial state of stress, right? And it's easy enough to check now that sigma n, of course, is equal to sigma bar n. Okay, so effectively this thing is also acting. Sigma bar is also an eigenvalue, and n is an eigenvector. Okay, and furthermore, if m belonging to R3 is such that m is perpendicular to n, okay, it follows that sigma m equals 0, right? Easy to check. All right. What this means is that now we have a surface in the body. If we consider any surface in the body, right, as long as that surface is oriented perpendicular to the n direction, we get a non-zero traction across that surface, right? If we consider any other surface, right? Not that one. If we consider in particular a surface that is perpendicular to n, like that one, right? Attraction across that surface is 0. Okay, so effectively what we have here is a stress that sort of acts only along the n direction. Okay, so easy enough. Okay, and then from here we can go on to the idea of a biaxial state of stress. Right? So for the biaxial state of stress, we have sigma equals sigma n tensor n plus sigma m tensor m. Okay? And of course now it's trivial, but you can go on to a triaxial state of stress by adding on another term of this type, where you use another vector that is perpendicular to n and m. Okay, and effectively we've reconstructed then the spectral decomposition of sigma. Okay, so let's just finish that up. Okay, m, n, and maybe L, right? I wrote them the wrong in the wrong order relative to the alphabet. Anyway, all belong to R3, right? And right. Let me just say that they form an orthonormal triad. And forming an orthonormal triad, right? Then we can say sigma equals sigma m tensor m plus sigma n tensor n plus sigma L tensor L. Let me make this clear. Okay, and really what we've done here is it turns out that m, n, and L are in fact the eigenvectors of the stress tensor in this case, and and sigma m, sigma n, sigma L are the eigenvalues. Okay. Finally, let's just look at what is often called a hydrostatic state of stress, right, which is a special case of the triaxial state, hydrostatic state of stress. Okay, this is when all three, or when sigma m, sigma n, sigma L are equal. Okay, so we can look at this as sigma equals, let's just say, let's just denote the common value is sigma bar. Okay, m tensor m plus n tensor n plus L tensor L. Now, a property of an orthonormal triad is that if you form the tensor product of each member with itself and add them up, you get back what? What is this? What is this sum? Think about it. It is the isotropic tensor. All right. So our hydrostatic state of stress is one in which we have sigma bar multiplying the isotropic tensor. Okay. what this means is that if we take our body and, right, we have this, if you were to go inside this body and now look at the traction along some direction n, right, where this arrow now denotes that direction n, some unit vector, right? You form the traction along any direction, right? You will get, well, you not only form the traction, but you also form the normal vector, right? The normal stress. The normal stress in every direction here, right? If this vector is n, you just form n dot sigma n in every direction. You will get exactly the same value, right? And this is the property of the second order isotropic tensor. What this means is that in every direction that you look inside the body, you find the same stress. Okay, and this is what happens if you are immersed inside a fluid, right? And the fluid is at rest. That's what you would see, and therefore it's called a hydrostatic state of stress. Okay, it's common in fluids. Okay. So what this means is that n dot sigma n equals sigma bar, as is easy to check, right, for all n. Okay, take any direction n, it's the same. All right. Oh, yes, one last thing. Let's just put down a general state of shear stress. Okay, so shear stress. Okay, as before, we have m and n are vectors, right, and they are perpendicular to each other, each of unit magnitude. Okay? In this case, what we have is that sigma equals, let's say, sigma s m tensor n plus n tensor m. Okay? That is a state of stress, a state of shear stress in the so-called MN plane. All right? Let's see how this works. If now we take sigma n, we would get sigma s m. Okay, so this is our body. Right, and we take a surface. If that is the n direction, okay, and this is n. The stress the traction that we get on the surface is in this direction. Okay, so let me just do this. What we have there is the traction sigma s m. All right. If on the other hand we took a surface perpendicular to the m direction, okay, what we would get is sigma m equals sigma s n, right? So then we would get that to be the traction vector. Okay. All right. Okay. So, and you know, clearly these are states of shear stress, right? On the two surfaces we've considered, we see that the effective traction is tangential to the surface, which is our notion of a shear stress. All right. And also note that we've taken care, we took care back here at the bottom of this slide to make sure that sigma, as defined here, is indeed symmetric. Okay.